The cosmos holds a terrifying beauty in the dark heart of a black hole. But what if its true opposite is not emptiness, but an explosive cosmic geyser, a white hole? These theoretical wonders are not cosmic vacuum cleaners, but cosmic fountains, violently pushing everything away. By the end of this journey, you will understand 50 astonishing facts about the universe's most distant and mysterious objects. We will explore if the Big Bang itself was a white hole and how they could solve the greatest paradox in physics. What cosmic mystery are you most curious to unravel? A white hole presents the ultimate cosmic one-way street, where a black hole is a bottomless pit from which nothing, not even light, can ever return. A white hole is its exact opposite, a cosmic source so repulsive that nothing from the outside can ever get in. Imagine trying to climb up an impossibly powerful waterfall. You could never reach the top, but the water itself gushes outward relentlessly. This is the essence of a white hole, a hypothetical region of space-time that violently expels matter and energy while completely prohibiting any entry. The mathematics of Einstein's theory of general relativity, the very same equations that predict the existence of black holes, also allow for this bizarre solution. In a purely theoretical sense, a white hole is simply a black hole running backwards in time. While we have gathered overwhelming evidence for black holes out in the universe, a true white hole has never been observed. It remains one of the most profound and puzzling what-if scenarios in all of physics, a cosmic geyser whose existence would force us to rewrite our understanding of reality itself. This cosmic one-way street is not a flight of fancy. White holes are not science fiction. They are legitimate, though entirely unproven, mathematical predictions. They emerge directly from the very same equations of Einstein's theory of general relativity that have so accurately foretold the existence of gravitational waves and the shadowy silhouettes of black holes. These are not separate ideas, but different faces of the same profound truth about how space-time behaves under extreme gravity. The mathematics does not care about our everyday intuition. It simply presents a complete picture, and within that picture, the possibility of a white hole is as real, in a theoretical sense, as the black holes we now observe. This gives white holes a firm, if deeply speculative, footing in the bedrock of modern physics. They are a ghost in the machine of the universe, a persistent echo in the equations that we cannot yet silence, forcing us to ask whether our universe might be stranger than we ever dreamed. This elegant symmetry reveals a profound secret about the universe. The laws of physics at their deepest level do not seem to favor one direction of time over the other. This principle is known as time reversal symmetry. Think of it like a simple film reel. If you were to record a perfectly normal event, like a ball bouncing on the floor, and then play that recording backwards, the motion would look bizarre and unnatural. The ball would appear to leap from the floor into your hand, defying gravity. Yet, the fundamental forces governing each individual collision, the transfer of energy, they would all still work perfectly. They are time-symmetric. Now, apply this idea to the most extreme object we know, a black hole. Imagine you have a film of a black hole actively devouring a cloud of glowing gas. You watch as the gas spirals inward, crossing the event horizon and vanishing from our universe. Now, run that film backwards. What would you see? You would witness a blinding eruption. That same gas would come bursting out from the central point, violently expelled into space. The black hole, running in reverse, becomes a white hole. This is not just a clever visual trick. It is embedded in the very mathematics of general relativity. The equations that describe the crushing gravity of a black hole are, in a sense, ambivalent about the flow of time. They permit this reversed version to exist as a theoretical possibility. So a white hole is not merely the opposite of a black hole. It is its mirror image in time, a cosmic echo from a reversed reality. If the laws of physics are so indifferent to time's arrow, Why does our universe seem to move relentlessly forward? The existence of a white hole would force us to confront that very question. This transformation hinges on the most extreme point in the universe, the singularity. Deep within a black hole at the very center, the known laws of physics break down completely. Matter is crushed into an infinitely dense, infinitely small point. This is the black hole singularity, a place where gravity becomes so overpowering that space-time itself ceases to exist as we understand it. But what if this is not the end of the story? Some of the most advanced theories in physics, particularly those attempting to unite general relativity with quantum mechanics, propose a radical alternative. They suggest that the immense gravitational collapse of a black hole singularity might not be a final state. Instead, the crushing force could reach a maximum and then rebound, like a spring compressed to its absolute limit. This theoretical event is called a quantum bounce. In this model, the black hole singularity does not simply vanish. It undergoes a profound metamorphosis, transforming into the explosive heart of a white hole. The point of infinite density would then become a source, not a sink. This creates a breathtaking cosmic bridge, linking the ultimate destruction of a black hole to the ultimate creation of a white hole. It proposes an entire life cycle for these objects, a cycle of gravitational collapse and explosive rebirth that could be happening across the cosmos, completely hidden from our view. If this is true, then every black hole could be a white hole in waiting, a cosmic seed preparing for a new beginning. This cosmic bridge might be more than just a theoretical loop. It could be a tunnel through the very fabric of space and time. The same mathematics that links a black hole to a white hole also describes a wormhole, often called an Einstein-Rosen bridge. Picture a vast tunnel with two distinct ends. On one side, a black hole acts as the entrance, a one-way door where matter and energy fall in. On the other side, far across the cosmos, the white hole serves as the exit, violently spewing that same matter and energy back out. This creates a complete, though incredibly unstable, shortcut through the universe. You could, in theory, jump into the black hole entrance and emerge moments later from the white hole exit in a galaxy millions of light years away. The journey through the tunnel, the wormhole throat, would bypass the normal expanse of space between the 2 points. This is not merely science fiction, but a direct consequence of solving Einstein's equations for gravity. The concept becomes even more profound when we consider the ultimate fate of the matter making this trip. What happens to a star or a person traversing this cosmic subway? The journey through the wormhole's throat would be catastrophically brief. The moment any matter enters the black hole, the delicate tunnel would collapse instantly. The gravitational forces at play would snap the bridge shut, crushing anything inside into an unrecognizable state long before it could reach the white hole exit. This is the great paradox of wormhole travel. The very act of using the tunnel guarantees its destruction. So while the white hole offers a tantalizing exit, getting to it through a black hole entrance remains a physical impossibility, a cosmic pathway that is perpetually closed by the laws of physics themselves. Yet, this startling connection forces us to wonder if the universe allows for other, more stable forms of travel we have not yet discovered. This relentless outward push defines the white hole's ultimate boundary, its event horizon. While a black hole's event horizon is a one-way street leading in, the white hole's is its perfect inversion, a one-way street leading out. Think of it as a cosmic exit-only door permanently locked from the outside. Any matter or energy that originates within the white hole can burst outward, crossing this threshold and shooting off into the wider universe. But for anything else, for any particle of dust, any beam of light, or any intrepid spacecraft trying to approach from the outside, this horizon is an utterly impenetrable wall. You could travel at the speed of light itself, and you would still be forever repelled, never able to cross over into the white hole's inner sanctum. This is not a matter of a powerful force field you could potentially overcome. It is a fundamental property of space-time itself, a permanent and unchangeable law of this bizarre object. The universe outside simply does not exist from the perspective of the white hole's interior. It is a cosmic island, forever isolated, forever pouring its contents out into a cosmos it can never welcome in. How could such a solitary object ever come to exist in the first place, if nothing from our universe can ever reach it? This permanent isolation creates a profound cosmic contradiction. White holes appear to break one of the universe's most fundamental rules, the second law of thermodynamics. This law states that the total disorder or entropy of a closed system must always increase over time. It is the reason a shattered glass does not spontaneously reassemble itself. A black hole perfectly obeys this law, acting as a cosmic trash compactor that takes in ordered matter and produces immense disorder. But a white hole does the opposite. It takes whatever is inside its hidden core and spews it out into the universe as a clean, ordered stream of energy and particles. This looks like a miraculous decrease in entropy, a cosmic violation that seems to make white holes physically impossible. How can an object make the universe more ordered? Physicists have proposed a fascinating resolution to this paradox. The key is to look at the complete picture, not just the white hole's final act. The immense order it releases must be paid for by an even greater amount of disorder created somewhere else. One compelling idea is that the formation of the white hole itself, perhaps through a quantum bounce from a black hole, generates a staggering, universe-shaking amount of entropy. All the chaos and destruction of the original collapse is not erased but is instead locked away, hidden from our view, acting as a counterweight to the ordered eruption we witness. Another possibility is that the very act of expulsion is not as clean as it seems. The matter bursting forth could be inherently unstable, instantly decaying into a far more chaotic state the moment it leaves the horizon. So while the white hole might appear to be a fountain of order, it is merely one half of a balanced cosmic equation, a temporary illusion of neatness that is utterly dependent on a hidden, monstrous mess. The second law of the universe remains unbroken, but it forces these theoretical objects to exist only under the most extreme and paradoxical conditions. This repulsive nature might hold the key to the universe's greatest mystery, dark energy. For decades, astronomers have known that the cosmos is not just expanding, but its expansion is accelerating at an ever-increasing rate. Some unknown force, dubbed dark energy, is pushing galaxies apart. But what if this force is not a new, exotic substance, but the accumulated effect of countless white holes? Imagine the universe is filled with an invisible population of these cosmic fountains, each one exerting a subtle, repulsive gravitational push on the space around it. While the gravity of a single white hole is incredibly localized, the combined effect of trillions of them scattered across the vastness of space could create a pervasive background force of repulsion. This force would act like a kind of cosmic pressure, stretching the fabric of spacetime itself and driving galaxies away from each other faster and faster. In this radical hypothesis, the mysterious dark energy is not a strange new field, but simply the long-range gravitational signature of the universe's most elusive objects. These white holes would not be the giant, violent eruptions we first imagined, but rather ancient, primordial relics from the very birth of the cosmos, so small and numerous that their individual pushes blend into a smooth, universal force. Their collective sigh could be the very breath that inflates our universe. This idea that white holes could explain dark energy is startling, but it pales in comparison to the most audacious proposal of all. Our entire universe, with all its galaxies, stars, and planets, might itself be the interior of a single colossal white hole. The Big Bang, the moment of creation for everything we know, could be the ultimate white hole eruption. Think about the characteristics of that primordial event. An unimaginably dense and energetic singularity suddenly, violently, expanded outward, spewing forth all the matter and energy that would eventually coalesce into the cosmos. This is not just similar to a white hole, it is a perfect match. In this radical model, the Big Bang was not an explosion in space, but the explosive birth of space itself from a point of infinite density. The entire history of our universe, from that first fiery moment to the present day, is simply the ongoing expansion of matter and energy from that initial white hole event horizon. We are not looking at white holes from the outside, we are living inside the biggest one of all. This provides a breathtakingly elegant potential answer to the greatest question: where did everything come from? If our universe is a white hole, then it must have formed from something else. The singularity that became our Big Bang could have been the end result of a gravitational collapse in a much larger parent universe. A giant star in that other cosmos could have died, collapsing into a black hole. But deep within that black hole, a quantum bounce occurred, transforming the crushing singularity into an explosive white hole, giving birth to our entire reality. We are not the main universe, but a cosmic offspring, a baby universe bubbling out from the demise of a star in a world we can never see. This idea forever redefines our place in the cosmos, suggesting that every black hole in our universe could be a portal to a new reality being born. This inherent instability presents a monumental problem for their existence. The pristine purity of a white hole, its perfect refusal to accept anything from the outside universe, is also its greatest weakness. Theoretical models strongly suggest that these objects are violently unstable, existing in a state of perpetual cosmic fragility. Imagine a perfect inverted dome made of the most fragile glass, repelling all dust and air. Now throw a single grain of sand against it. The entire structure would not just crack, it would shatter instantly. This is the fate predicted for a white hole. The moment any external matter, even a single photon of light, attempts to cross its forbidden horizon, it disrupts the delicate balance. That tiny, insignificant interaction would be enough to trigger a catastrophic collapse. The white hole's own immense energy and mass would turn inward upon itself, and in a flash of gravitational turmoil, the entire object would transform into a black hole. It would be a stunningly brief existence, a cosmic puff of smoke that vanishes as quickly as it appears. This fundamental instability is a primary reason why many physicists are deeply skeptical that long-lived white holes could ever exist in our dynamic, messy universe, which is filled with stray particles and radiation. How could such a delicate object survive for even a moment in a cosmos that is never truly empty? This cosmic fragility points to a deeper truth, that white holes are not creatures of Einstein's gravity alone. Their existence likely hinges on a more complete picture of reality, a theory of quantum gravity. Einstein's general relativity gives us the majestic landscape of space-time, but it fails at the most extreme point, the singularity. Here, where density becomes infinite, the equations simply break down, offering no answers. This is where quantum gravity must take over. This sought-after theory aims to unite the vast cosmic rules of relativity with the bizarre, probabilistic laws that govern the tiny quantum world. It is within this unified framework that white holes could find a stable home. One leading candidate, called loop quantum gravity, provides a stunning possibility. It suggests that at the very core of a black hole, the crushing gravitational collapse does not end in a true singularity. Instead, the fabric of spacetime is woven from tiny, finite loops. This quantum structure acts like a cosmic cushion, preventing the infinite collapse. The immense pressure reaches a maximum and then, inevitably, rebounds. In this model, every black hole does not remain a black hole forever. After a certain period, which could be astonishingly long, it would undergo a quantum transition, transforming directly into a white hole. This is not a violent instability triggered from the outside, but a natural and fundamental phase change built into the very fabric of the cosmos. The black hole's event horizon would effectively vanish, replaced by the explosive outflow of a white hole horizon. This means white holes would not be rare anomalies, but the ultimate fate of every black hole, a final act of cosmic rebirth written into the laws of physics themselves. If this is correct, then the universe could be filled with the ancient, fading remnants of white holes, each one a silent testament to a star that died twice. Despite their profound theoretical possibility, the cosmos has yet to offer up a single confirmed white hole for us to see. We have zero direct observational evidence that they exist. Astronomers are actively searching the skies for their unique signatures, knowing exactly what to look for. A white hole eruption would be an event of staggering power, a sudden, brilliant flash of high-energy radiation and particles bursting forth from a single point in space with no apparent cause. It would look like a cosmic geyser turning on without warning. Researchers also comb through the faint afterglow of the Big Bang, the cosmic microwave background, searching for any subtle imprints or patterns that could be the fossilized remnants of primordial white holes from the universe's infancy. Yet, despite decades of looking and several tantalizing false alarms, no candidate has withstood the rigorous scrutiny of follow-up observations. Every potential white hole signal has, upon closer inspection, been explained by something more conventional, like a supernova, a gamma-ray burst, or a collision between neutron stars. This enduring absence is not a dismissal of the idea, but rather a deepening of the mystery. It forces us to ask whether white holes are simply too rare, too brief, or too well hidden for our current telescopes to find, or if the universe is guarding this particular secret more closely than any other. Gamma-ray bursts are the universe's most powerful explosions since the Big Bang itself. In a fleeting moment, one can outshine an entire galaxy, releasing more energy than our sun will emit over its entire 10 billion-year lifetime. For a few precious seconds, these brilliant flashes dominate the gamma-ray sky, appearing to come from a single, incredibly distant point. When they were first discovered by military satellites in the 1960s, their origin was a complete enigma. The sheer violence and the sudden, one-way outpouring of energy from a seemingly empty point in space perfectly matches the theoretical signature of a white hole eruption. It is as if a cosmic faucet was turned on at full force for a brief, blinding instant, then shut off forever. Could these be the long-sought-after white holes making their brief, catastrophic appearance on the cosmic stage? For a time, this was a compelling possibility. The idea that we were witnessing the final, explosive death throes of a black hole reborn as a white hole captivated many theorists. The white hole model provided a neat, if spectacular, explanation for the immense, focused energy and the lack of any visible progenitor star. However, as our observational tools grew sharper, the story became more complicated. The vast majority of gamma-ray bursts have now been firmly linked to other, more conventional cosmic cataclysms. Long-duration bursts are now understood to be the birth cries of black holes, signaling the collapse of massive stars in supernova events. Short-duration bursts are almost certainly the violent mergers of ultra-dense neutron stars, shaking the fabric of space-time and creating gravitational waves. In both cases, we have observed the afterglow in other wavelengths of light, linking the burst to a specific chaotic event in a distant galaxy. Yet a stubborn few bursts remain enigmatic. Astronomers refer to them as naked or orphan gamma-ray bursts. These events lack the characteristic afterglow or the accompanying supernova that would neatly explain their origin. They flash into existence from the void and then vanish without a trace, leaving no visible remnant behind. It is within this strange, unclassified minority that the ghost of the white hole theory still lingers. Could these be the true, unstable white holes, flashing into existence for a single, glorious moment before collapsing into the black holes that general relativity predicts? They remain the universe's most powerful and perplexing mysteries, a reminder that our catalogue of cosmic explosions may still have a few blank pages waiting to be filled. This absence of an accretion disk creates a profound visual paradox. We are accustomed to identifying black holes indirectly by the intense, whirling maelstrom of superheated gas and dust that spirals into them. That brilliant, flat disk is the signature of matter being torn apart and devoured. A white hole presents the exact opposite spectacle. Since its event horizon repels all incoming matter, nothing can form a stable orbit or spiral inward. There is no cosmic feast, only a cosmic fountain. This means a white hole would appear not as a dark shadow circled by fire, but as a stark, isolated point of blinding light. It would be a brilliant beacon erupting from the void, with no surrounding structure to explain its existence. Imagine a single, impossibly bright star that flickers and pulses with high-energy radiation, yet sits in perfect, empty darkness. Any stray interstellar gas or dust that drifted near this object would not fall inwards to create a glowing disk. Instead, it would be violently pushed away, swept aside by the white hole's relentless outward pressure. This pure, unadorned eruption is what would make a white hole so unique and so difficult to find. Its light would have no context, no accompanying story of destruction. It would simply be a solitary mystery against the black velvet of space. How would you even begin to classify such an object, a star that refuses to be fed? This brilliant, solitary light could be hiding the universe's deepest secret, the preservation of information itself. White holes may offer the only escape from a paradox that threatened to unravel modern physics, the black hole information paradox. The problem begins with a simple question. What happens to the information about an object that falls into a black hole? Imagine you throw a book into a fire. The book burns to ash, but in principle, a being with perfect knowledge could analyze the smoke, the heat, and the remaining ashes to reconstruct every single word that was written on its pages. The information is scrambled, but it is not truly gone. Now, throw that same book into a black hole. According to Stephen Hawking's groundbreaking work, black holes are not completely black. They slowly evaporate over astronomical timescales, emitting a faint whisper of radiation now called Hawking radiation. The devastating conclusion Hawking reached was that this radiation is entirely random, a featureless thermal haze. It carries no information whatsoever about the original book, or the star, or the astronaut that fell in. When the black hole finally evaporates and vanishes, all the intricate information about everything it ever consumed is erased from the universe forever. This violates a cornerstone of quantum mechanics, which states that information must always be preserved. It can never be truly created or destroyed, only transformed. Hawking's idea meant that our most fundamental understanding of reality was wrong, and physicists have been grappling with this terrifying implication for decades. How can the universe simply forget? The potential solution is as elegant as it is radical. What if the information is not lost but is instead trapped, waiting for a cosmic jailbreak? This is where the white hole enters the story. If a black hole does not simply evaporate into nothingness, but instead undergoes a quantum bounce to become a white hole, then the final act of this transformation is not a silent disappearance. It is a grand, explosive release. In this scenario, all the information that was ever funneled into the black hole, all the quantum details of every particle, gets locked away during its black hole phase. It is imprinted onto the very fabric of the new white hole structure. Then, when the white hole erupts, that information is not lost. It is encoded into the matter and radiation that comes blasting out. The random thermal radiation Hawking predicted would merely be the prelude. The main event would be the white hole's final burst, which would carry a perfect, though incredibly scrambled, record of everything that fell in. The universe would not forget. It would simply be storing the information in a vault of gravity, waiting to return it in a spectacular final flash. The white hole becomes the universe's ultimate librarian, ensuring that not a single cosmic story is ever permanently erased. This same explosive release could be the key to another, more recent cosmic puzzle. Across the universe, astronomers detect fleeting blips of radio energy so powerful they can be seen from billions of light years away. These are fast radio bursts, mysterious millisecond flashes that appear without warning and then vanish. Their source remains one of the most active and confusing chases in modern astronomy. The sheer energy packed into such a brief instant is staggering, requiring an engine of almost unimaginable efficiency. What natural process can create such a brilliant, focused, and vanishingly short signal? The answer might lie in the smallest possible white holes. Imagine a white hole not as a colossal cosmic fountain, but as a subatomic spark. Theoretical models suggest that microscopic white holes could pop into existence for a fraction of a second, erupting with the entire energy of their brief lives in one single catastrophic pulse. This would be the ultimate example of white hole instability, a life measured in milliseconds. The eruption would channel all its energy into a tight beam of radiation, a final, defiant shout into the cosmos before the object collapses into a black hole and vanishes completely. The entire event, from birth to explosive death, would perfectly match the profile of a fast radio burst. It would be a brilliant, one-time flash with no visible remnant, a ghost in the radio static. While most astronomers favor more conventional explanations involving highly magnetized neutron stars, the exotic possibility remains. Could these enigmatic signals be the death cries of the universe's tiniest and most ephemeral white holes, each one a universe in miniature breathing its last? This naked singularity is the ultimate rule breaker in the cosmos. Deep within a black hole, the crushing point of infinite density is safely hidden behind the one-way curtain of the event horizon. Its bizarre, law-breaking physics are locked away, unable to affect our universe. But a white hole turns this protective shielding inside out, because a white hole's event horizon violently repels everything from the outside. Its central singularity is completely exposed. It is naked. A naked singularity is a point where the known laws of physics cease to exist, sitting out in the open for anyone to see and potentially interact with. This is a terrifying prospect for a physicist. At a singularity, gravity becomes infinite and the smooth fabric of space-time tears apart. Cause and effect, the very basis of prediction and science, could break down entirely. If you could send a probe towards a naked singularity, its fate would be utterly unpredictable. It might be vaporized, it might be twisted into a new form of matter, or it might emerge speaking in riddles. The physics becomes pure chaos, and that kind of unpredictability is something the universe seems to abhor. This profound problem led the renowned physicist Roger Penrose to propose the cosmic censorship hypothesis. This is not a formal law, but a powerful conjecture that nature itself forbids the existence of naked singularities. It suggests a cosmic rule that every singularity must be modestly clothed, forever hidden behind an event horizon. The universe, in this view, acts as a cautious censor, protecting the orderly realm of predictable physics from the anarchic core of these infinite points. For white holes, this is a devastating verdict. A classical white hole, by its very definition, possesses a naked singularity. Its entire structure is a violation of cosmic censorship. If Penrose's hypothesis is correct, then true white holes simply cannot form or exist in our universe. They would be stillborn, collapsing into black holes the instant they tried to appear. This is one of the strongest arguments against their reality, yet the final word on cosmic censorship is not yet written. The hypothesis remains unproven. Some theories of quantum gravity suggest that at the very smallest scales, the concept of a sharp, infinitely dense point might be an illusion. The singularity could be replaced by a fuzzy quantum core, a region of extreme but finite density where physics remains sane. In this scenario, a white hole might not have a true naked singularity after all, but rather a stable quantum heart. Its event horizon could then be a gateway to this bizarre but predictable quantum region. The debate over naked singularities is really a battle for the soul of physics itself, questioning whether the universe demands order at all costs, or if it allows for islands of beautiful, terrifying chaos. The gravity of a white hole is just as real as a black hole's. It still pulls. This is a vital distinction to grasp. A black hole is often mislabeled as a cosmic vacuum cleaner, actively sucking everything in. But that is not quite right either. A black hole's gravity simply creates a steep pit in spacetime, and objects fall in naturally like a marble rolling down a funnel. A white hole creates the exact same gravitational pit. The difference is not in the pull of gravity, but in the nature of the floor. In a white hole, the bottom of that pit is not a passive point of no return. It is an active, explosive engine. Imagine a fountain at the bottom of a deep well. You are drawn toward the well by gravity, but as you get closer, you are met with a powerful, continuous jet of water blasting upward. No matter how hard you try to fall in, that immense outward pressure violently repels you. The water does not suck you in, it pushes you away. A white hole operates on a cosmic scale. Its interior is a maelstrom of radiation and energy under such incomprehensible pressure that it acts like a force field, overpowering the inward tug of its own gravity at the event horizon. So while the white hole's mass does attract you from a distance, its fundamental nature ensures you can never get close enough to truly feel that pull. It is a cosmic repulsor, not an anti-gravity device, a geyser whose very existence defies the simple act of falling. These same cosmic fountains could be the ultimate particle accelerators of the universe. We are constantly bombarded by a silent, invisible rain from space, a shower of atomic fragments traveling at nearly the speed of light. These are cosmic rays, and the most energetic among them carry more punch than anything we can create on Earth. A single one of these ultra-high energy particles can possess the kinetic energy of a professionally thrown baseball, all compressed into a single subatomic speck. For decades, their origin has been a profound mystery. What cosmic engine is powerful enough to fling a proton with such unimaginable force? The answer might lie in the violent heart of a white hole. Picture the moment of eruption when matter and radiation are blasted outward from the singularity. The forces at play near that point are beyond comprehension, creating gravitational and electromagnetic fields of staggering intensity. A stray proton or atomic nucleus caught in this maelstrom would be whipped and torn, gaining tremendous energy as it is accelerated along these chaotic fields. It would be like a tiny pebble caught in the exhaust of a cosmic rocket, shot out into the void at a velocity approaching the ultimate cosmic speed limit. The white hole would act as a natural particle cannon, firing its high-energy ammunition across millions of light years. These particles would travel for eons, their paths bent by magnetic fields until one finally, randomly, slams into our atmosphere. The collision creates a secondary shower of particles, a faint echo of the white hole's ancient fury that we can detect on the ground. While other sources like active galactic nuclei are strong candidates, the white hole offers a uniquely potent and focused engine for the very highest energy events we see. Its brief, catastrophic existence could be the very source of the universe's most powerful subatomic bullets. This reversal of time shatters our most basic assumption about reality, the unbreakable chain of cause and effect. In our everyday world, a cause always comes before its effect. You throw a rock, a window breaks, the throw is the cause, the breaking is the effect. This sequence is the bedrock of logic and science, but a white hole, as a black hole running backwards in time, turns this sequence on its head. Imagine witnessing a white hole eruption. You see a brilliant flash of light and a stream of high-energy particles burst forth from nothingness. In our normal timeline, we would search for a cause for this event, something that made it happen. But if this is truly the time reverse of a black hole, then the cause of the eruption lies in its future, not its past. The matter that erupts out was not assembled and then exploded. Instead, it is as if the final, explosive state of the white hole reaches backwards in time to dictate its own beginning. The effect creates the cause. This is not mere philosophical speculation. It is a direct consequence of the time-symmetric mathematics of general relativity. The equations allow for a universe where the future can reach back and influence the past, a concept that makes our brains recoil. It suggests that the arrow of time we experience so powerfully might be a local illusion, a feature of our particular corner of a much weirder cosmos. If white holes exist, they are not just cosmic objects, they are cracks in the foundation of causality itself, forcing us to question whether the flow of time is a fundamental river or just a gentle current in a much stranger ocean. The sheer violence of a white hole eruption defies all known benchmarks of cosmic power. Its energy output would not merely be large, it would be absolute, a fundamental release tied directly to the object's mass. This is not like a star burning through its fuel over millions of years. A white hole's eruption is a single, catastrophic event where a significant portion of its entire mass is converted directly into pure energy, following Einstein's most famous equation. The theoretical limits are almost incomprehensible. A white hole with the mass of our Sun would, in its brief explosive phase, release more energy than every star in the Milky Way galaxy combined, all shining at their absolute brightest for that single blinding moment. It would be a cosmic flashbulb so intense it could temporarily outshine the collective light of 100 billion suns. To put this on a more familiar scale, consider a supernova, the violent death of a massive star. A supernova can outshine its entire host galaxy for a few weeks. A white hole eruption would outshine not just one galaxy, but potentially thousands of them for a similar duration. Or take a quasar, the incredibly luminous core of a distant galaxy, powered by a supermassive black hole feasting on gas. A quasar's brilliance can be seen across the universe. A white hole of equivalent mass would dwarf it, not through a slow, continuous feast, but in one single, definitive burst of creation. This is the ultimate difference. A quasar is a cosmic engine of consumption, while a white hole is an engine of pure, unadulterated birth, and its first cry would be the loudest sound the universe has heard since its own beginning. These ancient relics might be the universe's original white holes. While most theories focus on white holes born from black holes, another path to their existence bypasses stellar death entirely. In the first fleeting moments after the Big Bang, the cosmos was not smooth and uniform. It was a seething, turbulent sea of energy, riddled with violent density fluctuations. In some regions, the infant universe was so intensely packed that gravity could have crushed matter directly into primordial black holes. This same chaotic process could have worked in reverse, creating regions of such extreme outward pressure that they pinched off into primordial white holes. These objects would not be the children of dying stars, but the siblings of the Big Bang itself, fossils from the universe's first seconds of existence. They would be incredibly small, perhaps with the mass of a mountain compressed into a space smaller than an atom, yet possessing the fundamental nature of a true white hole. For billions of years, these primordial white holes would have drifted through the cosmos like silent ghosts, their immense mass tugging subtly on stars and galaxies, but otherwise remaining completely invisible and stable. Their eventual fate, however, would be a final, spectacular act of cosmic revelation. A primordial white hole would not last forever. governed by the same quantum processes as a black hole, it would slowly evaporate over eons, losing mass until it reached a critical point. At that threshold, the entire object would erupt in a final, catastrophic burst of energy, converting its remaining mass into a blinding flash of gamma rays and high-energy particles. This would not be the gentle sigh of evaporation, but the definitive death cry of a cosmic fossil. We could be witnessing these events right now in the form of unexplained, high-energy flashes from empty space. The sudden, powerful burst from a primordial white hole's demise would be a unique fingerprint, a signal of an ancient relic from the dawn of time breathing its last. This spectacularly brief existence defines the white hole's entire life cycle as a single explosive event. While a black hole can persist for trillions of years, slowly fading through Hawking radiation, a white hole's story is written in a single blinding sentence. Its formation, whether from a quantum bounce or as a primordial relic, is immediately followed by its destruction. The moment it comes into being, the immense pressure bottled up within its core violently overcomes its own gravity. The event horizon, that perfect one-way exit door, shatters. All the matter and energy the white hole contained, its entire mass, is converted directly into a cataclysmic burst of radiation and particles. This is not a slow leak, but a total and instantaneous release. For a white hole with the mass of our Sun, this entire process would be over in a fraction of a nanosecond. A life measured in the blink of a cosmic eye. The result is a final, definitive pop, a flash of light and energy so concentrated it would briefly outshine entire galactic clusters. This is the ultimate difference between these cosmic twins. A black hole is a long, slow fade to black, a gravitational sigh that lasts for eons. A white hole is a sudden, brilliant flash of lightning against the dark cosmic sky, there and gone in an instant, leaving nothing but an echo of its violent birth and immediate death. This fundamental difference in their birth separates the cosmic twins forever. A black hole is the direct and violent result of a star's death, a corpse left behind after a supernova explosion. When a truly massive star, many times heavier than our Sun, exhausts its nuclear fuel, the outward pressure that has supported it for millions of years suddenly vanishes. The star's own immense gravity, no longer held in check, causes a catastrophic collapse. The core implodes, crushing itself into a point of infinite density, while the outer layers are blasted away in a titanic explosion. What remains is a black hole, a gravitational scar in space-time. This is a process we can observe, a natural endpoint for stellar evolution. A white hole cannot be born this way. There is no known stellar process, no death of a star, that could possibly create an object that only expels matter and energy. You cannot get a cosmic fountain from a cosmic collapse. So if white holes are real, they must come into existence through far more exotic means. One possibility is that they are primordial, forged in the unimaginable conditions of the Big Bang itself, cosmic fossils from the very first instant of time. The other, even more mind-bending possibility is that they are not born from stars at all, but from the corpses of stars. A white hole could be the ultimate rebirth, the quantum resurrection of a black hole after an almost endless period of dormancy. This means a white hole is not just an opposite, it is a successor, a second life granted by the bizarre laws of quantum gravity. While we can point our telescopes at dying stars and watch black holes form, the birth of a white hole would be a silent, hidden event, either lost in the heat of creation or occurring in the quantum shadows of a pre-existing grave. This mathematical beauty is not a minor detail, but the very heart of the white hole's mystery. The equations of general relativity do not simply tolerate the idea of a white hole, they almost demand its consideration as a logical and elegant counterpart. The theory paints a complete picture of space-time, and within that grand canvas, the black hole and the white hole are two sides of the same breathtaking coin. Their symmetrical existence in the math points toward a universe governed by profound and beautiful rules. a cosmos where every action has an equal and opposite reaction woven into the fabric of reality itself. This forces physicists to ask uncomfortable, foundational questions. Why does our observed universe seem to favor black holes, the cosmic consumers, while their pristine twins, the cosmic fountains, remain hidden? Is this a fundamental asymmetry in the laws of nature, or is it merely a feature of our particular cosmic history, a quirk of how our universe cooled from the Big Bang? The relentless pressure of this mathematical elegance pushes theoretical progress forward, compelling scientists to develop new ideas like the quantum bounce, to bridge the gap between the beautiful symmetry of the equations and the seemingly lopsided reality we observe. The white hole, real or not, serves as a permanent mathematical compass pointing toward a deeper, more complete understanding of everything. Our journey into Einstein's universe reveals a compelling symmetry, but what happens when we step beyond his equations? The search for white holes does not end with general relativity. In fact, some of the most promising places to find them lie within the daring theories that seek to replace or extend it. Take string theory, for instance, which proposes that the fundamental particles of the universe are not points, but tiny, vibrating strings. In this rich theoretical landscape, the fabric of space-time can develop intricate structures, including potential bridges between black holes and white holes that are far more stable than the fragile tunnels of classical physics. These cosmic shortcuts might not snap shut instantly, offering a glimmer of hope for the possibility of traversal. Elsewhere, in certain models of modified gravity, where Einstein's theory is tweaked to explain dark matter or dark energy without invoking new particles, white holes can emerge as natural and even necessary components of the cosmos. They are no longer bizarre outliers, but integrated features of a revised gravitational law. This evolution is crucial to grasp. The properties and even the likelihood of white holes are not fixed. They change dramatically depending on the theoretical lens we use to view the universe. A white hole in loop quantum gravity, born from a bounce, is a different beast from a white hole in a string theory landscape or a modified gravity framework. This tells us something profound about the nature of scientific discovery. Our cosmic imagination is limited only by the models we build. As we refine our equations to solve other great mysteries, the white hole transforms from a mathematical ghost into a potential prediction, waiting for its moment to shine in the light of a new theory. This cosmic tunnel leads to a reality beyond our own. The maximally extended Schwarzschild solution is a complete mathematical map of a simple black hole spacetime, and it reveals a geometry far stranger than a mere pit. Within this framework, the black hole is not a dead end. Instead, it forms one mouth of a bridge, a wormhole, whose other mouth is a white hole residing in a universe completely separate from our own. You would not travel to another point in our cosmos. You would exit into an entirely different spacetime, a parallel reality with its own distinct history and physical laws. Falling through this bridge would be a one-way trip into another creation. The journey itself defies conventional geometry. The tunnel or throat of the wormhole does not exist within the three-dimensional space we know. It is a shortcut through a higher dimension, a fold in the cosmic fabric connecting two distant sheets. From our perspective, you vanish into the black hole's event horizon. From the perspective of the other universe, you are spontaneously born from the white hole's horizon, an arrival from a place they can never visit or even detect. This is the ultimate expression of the black hole-white hole symmetry, not just a reversal in time, but a gateway to another existence. Your departure from our universe becomes the origin story for another. A black hole's slow fade into nothingness is one of its most haunting features. This process, known as Hawking radiation, suggests that over trillions of years, even the most massive black hole will gradually shrink, losing mass until it finally vanishes in a final tiny pop. This evaporation is a quantum quirk, a subtle leak in its gravitational armor. a white hole presents a completely different endgame. It would not produce Hawking radiation in the traditional sense at all. The reason lies in its fundamental nature. Hawking radiation depends on the black hole being a perfect black body, an object that absorbs everything and emits radiation solely due to quantum effects at its event horizon. A white hole is the antithesis of a black body. It is a brilliant, active source, a geyser of energy and particles. Its event horizon is not a surface that absorbs quantum fluctuations, but a boundary that violently expels them. The entire mechanism that powers Hawking radiation is inverted or perhaps even silenced. So how does a white hole die if not by evaporation? Its demise is not a slow leak but a catastrophic burst. All the energy and mass it contains since its formation is destined for a single, spectacular release. Its entire life cycle is a countdown to one definitive explosion. While a black hole whispers its way into oblivion, a white hole would scream its way out of existence, leaving no slowly fading remnant, only a brilliant and final flash etched into the fabric of space-time. This violent boundary between creation and chaos is a perfect laboratory for the universe's strangest rules. White holes offer a unique testing ground for quantum mechanics, allowing physicists to push the laws of the very small into the most extreme gravitational environments imaginable. Think of it like a cosmic wind tunnel. Just as engineers test a new aircraft design against hurricane-force winds, theoretical physicists can use the white hole model to test quantum theory against the ultimate outward pressure. The key question is how quantum fields, the invisible energy fields that make up all particles, behave when they are caught in the maelstrom of a white hole's event horizon. In a black hole, the intense inward gravity pulls on these fields, stretching them in ways that lead to Hawking radiation. But in a white hole, the effect is reversed. The fields are not being pulled in, they are being violently pushed out. This creates a completely different set of quantum effects at the horizon. By studying this theoretical interaction, scientists can explore how information is scrambled and potentially recovered, how particles are born from pure energy, and whether the laws of quantum physics hold firm when gravity itself is turned inside out. The insights gained are not just about white holes. They ripple outward, helping us understand how quantum mechanics and gravity fit together everywhere, from the first moments of the Big Bang to the quiet vacuum of empty space. This bizarre object becomes a lens, focusing our questions about the fundamental nature of reality itself. This inherent need for a predetermined state strikes at a deep philosophical puzzle. For any object in our universe, its present condition is the direct result of past events, a chain of cause and effect. A black hole perfectly embodies this principle. Its final properties, its mass, its spin, are entirely determined by the star that collapsed to form it and whatever unfortunate matter later fell in. Its history is written in its present state. A white hole shatters this logic. Since nothing can ever enter it from our universe, its explosive output cannot be the consequence of any prior event we can observe. The specific mix of particles and energy it erupts with must be set from the very moment it comes into being. It is born with a complete, pre-loaded script for its entire existence. This presents a profound challenge. How does nature decide what a white hole will be? What law or mechanism determines the exact recipe of its outburst without any prior external cause? It suggests a cosmic object that is somehow outside the normal flow of time, an entity whose entire life is predetermined in a single, causal moment of creation. This feels deeply unnatural within our understanding of physics, where objects evolve and change based on interactions. A white hole, in its purest form, would be a frozen sculpture of an explosion, its fate sealed before its first moment of existence, playing out a program written by a hand we cannot see. This idea that our cosmos is a newborn universe, birthed from a white hole in a larger parent reality, completely reshapes the entire concept of existence. It suggests that the Big Bang was not a unique, singular event, but a single blossom on an infinite cosmic tree. This is the multiverse hypothesis in its most physical form, a vast landscape of realities, each one potentially born from the gravitational collapse of a star in a universe above it. In this breathtaking model, white holes are not just objects within a universe, they are the very conduits of creation, the umbilical cords connecting a limitless family of cosmic realms. Each of these baby universes could be wildly different from our own. The fundamental constants, the strength of gravity, the number of dimensions, even the very laws of physics we consider immutable, could be set randomly during that initial white hole eruption. In one universe, gravity might be so strong that stars burn out in 1,000,000 years, while in another, atomic bonds might be too weak for planets to ever form. Our universe, with its perfect balance allowing for stars, planets, and life, would be just one favorable roll of the cosmic dice in an endless casino of possibilities. This places white holes at the very heart of cosmogenesis, the study of cosmic birth. They become the engines of a fecund, self-replicating metacosmos, where every black hole in every universe is a potential seed for a new reality, a new set of physical laws, forever branching outward into an unimaginable plurality of existence. Are we living in just one room of an infinite cosmic mansion, and is every door a white hole waiting to open? The elegant simplicity of a black hole is captured in the no-hair theorem. This cornerstone of general relativity declares that a black hole is fundamentally bald, stripped of all complexity. No matter what you throw into it, whether it is a cloud of hydrogen, a diamond, or an entire library, the resulting black hole forgets every detail. It sheds all information about the original matter, retaining only 3 defining features: its mass, its electric charge, and its spin. A black hole has no memory, no history, no hair. This theorem paints a picture of profound cosmic simplicity, where the most complex objects are reduced to their barest gravitational essence. But a white hole threatens to unravel this beautiful idea. If a black hole can transform into a white hole through a quantum bounce, then that process cannot be a simple reversal. The information about everything that fell into the black hole, the quantum identity of every atom, cannot simply vanish. It must be preserved, stored somehow during the black hole phase, and then imprinted onto the structure of the new white hole. This would give the white hole hair a complex and detailed record of its origin. The white hole would not be simple. It would be a cosmic archive, its very being etched with the story of its past. This challenges the no-hair theorem at its core, suggesting that black holes are not the final, simple endpoints we thought they were, but rather temporary vaults, holding information in trust for a future explosive release. The universe, it seems, may not believe in forgetting after all. The very heart of a white hole might be a cosmic factory for the universe's rarest substance, antimatter. This is not ordinary matter being expelled. The conditions near that naked singularity are so extreme, so far beyond any star or supernova, that they could fundamentally twist the fabric of particle creation. In our universe, for reasons we still do not fully understand, matter won a decisive victory over antimatter in the first moments of the Big Bang. For every billion particles of antimatter created, there were 1,000,001 particles of matter. That 1 in a billion imbalance is everything we see, from the farthest galaxy to the screen you're watching now. The rest annihilated in a flash of pure energy, leaving behind a cosmos dominated by matter. But why did this happen? White holes offer a speculative yet compelling answer. The singularity at a white hole's core is a place where the known laws of particle physics are rewritten by immense gravitational and quantum forces. In that chaotic forge, the processes that usually favor matter might be inverted or skewed. A white hole eruption could, in theory, produce a perfect 50-50 mix of matter and antimatter. Or, even more intriguingly, it could produce a surplus of antimatter, As this fountain of particles bursts outward, the matter and antimatter within it would immediately begin to annihilate upon contact, fueling the eruption with even more catastrophic energy. This constant internal annihilation would be the white hole's power source, a self-sustaining engine of destruction that transforms mass into pure radiant fury. The brilliant flash we would see from across the cosmos would be the light from this matter-antimatter Armageddon. If this is true, then white holes are not just cosmic fountains, they are the universe's primary antimatter foundries. The reason we find so little antimatter today is because white holes in their spectacular deaths consumed it all, leaving behind a universe sculpted from the leftover matter. Their violent ends could be the very reason for our material existence. This same violent boundary might guard its secrets with a wall of pure energy, a white hole firewall. The paradox arises from a deep conflict between Einstein's general relativity and the laws of quantum mechanics. For a black hole, the firewall idea suggests that the event horizon is not a smooth, empty gateway, but a searing wall of high-energy particles that would instantly incinerate anything falling in. This solves one quantum problem but shatters the principle of equivalence, a core tenet of relativity which states that an astronaut crossing the horizon should feel nothing unusual. Now apply this same logic to a white hole. What happens to the quantum fields at its explosive edge? As matter and energy are violently expelled, the horizon could act like a cosmic filter. But what is the condition of space right at that point of no entry? One possibility is that the immense outward pressure creates its own kind of firewall, a barrier of intense radiation facing the outside universe. This would not be a wall you could see or approach, but a fundamental property of the erupting boundary. The debate hinges on how information behaves. If a white hole is indeed the final stage of a black hole's life, then all the information it ever swallowed must be encoded in its final burst. The firewall could be the mechanism for this ultimate cosmic shredding and reassembly, scrambling quantum information into the outgoing radiation. Yet, this creates a baffling contradiction. Is the white hole's horizon a smooth, predictable surface as relativity demands, or is it a chaotic, energetic inferno as some quantum theories suggest? This paradox remains one of the most contentious and unresolved questions in theoretical physics, a ghost in the machine of gravity itself. The name itself is a cosmic misdirection, suggesting an object made of some brilliant white material. But a white hole is not a hole filled with white stuff any more than a black hole is a hole filled with black paint. The color label is purely symbolic, a shorthand for its fundamental opposition to a black hole's nature. One is a perfect absorber, the other a perfect emitter. The actual color of the light blazing from a white hole's eruption would be a product of sheer physics, not a namesake. It would be determined by the staggering temperature and ferocious energy of the matter and radiation being violently expelled. This matter, superheated to billions of degrees, would glow across the entire electromagnetic spectrum. It could shine with the searing blue-white intensity of the hottest stars, or it could radiate invisible but immensely powerful gamma rays. The color we would perceive, if our eyes could survive the glare, would simply be the visible slice of a much broader, catastrophic energy output. A white hole might not look white at all. It could appear as a brilliant violet pinprick or an ominous, deep red celestial beacon, its hue a direct window into the unbelievable forces at work within its heart. This cosmic rebirth finds its most rigorous form in a theory called loop quantum cosmology. It takes the mind-bending concept of a quantum bounce and builds an entire mathematical universe around it. According to this framework, the Big Bang was not a true beginning from nothing. It was a monumental transition, a great bounce from a previous cosmic phase that had been contracting under its own immense gravity. Picture the entire universe not as a single expanding balloon, but as a cosmic lung, inhaling for eons until it reaches a maximum density, then exhaling outward in the event we call the Big Bang. The moment of the bounce, the point of maximum compression, is where loop quantum cosmology makes its most stunning prediction. The crushing gravitational collapse does not end in a meaningless singularity. Instead, the fabric of space-time, woven from finite, indivisible loops, acts like a super-dense cushion. The repulsive force generated at this quantum scale becomes so powerful that it overwhelms the pull of gravity, forcing the entire universe to rebound. This critical transition point, this moment of cosmic reversal, behaves in every way like a white hole. It is a boundary where matter and energy, once falling inward, are now violently and irrevocably expelled outward, birthing a new cosmic epoch. Here, the white hole is no longer a speculative ghost in the equations of general relativity. It becomes the very engine of cosmic resurrection, a fundamental phase of the universe's cyclical life, grounded in the precise mathematics of quantum geometry. This gives the white hole a firm, predictive home in one of the most advanced theories of our time, transforming it from a fascinating what-if into a potential what was for our entire reality. This bizarre reversal of time opens the door to the universe's greatest taboo, time travel itself. The theoretical bridge linking a black hole to a white hole is not just a tunnel through space, but a potential loop through time. The mathematics of these wormholes often includes what physicists call closed time-like curves. These are paths through the fabric of space-time that bend so severely they actually curve back on themselves, like an ant walking along a Möbius strip. If you were to follow such a path, you would not travel to a new location, but back to a moment in your own past. The entrance of the black hole and the exit of the white hole could be connected not just across space, but across time, creating a cosmic shortcut to yesterday. This is not mere science fiction fantasy, but a genuine, if deeply disturbing, prediction that emerges from Einstein's own equations. The universe's rulebook, it seems, does not explicitly forbid a journey into the past. But this possibility immediately shatters our most fundamental understanding of reality. It creates the infamous grandfather paradox. What would happen if you traveled back in time and accidentally prevented your own grandfather from meeting your grandmother? You would never be born, which means you could never have traveled back in time to stop the meeting in the first place. The event becomes a logical loop with no beginning and no end, a cosmic contradiction that makes cause and effect utterly meaningless. The laws of physics seem to abhor such chaos. To resolve this, the legendary Stephen Hawking proposed a daring idea, the chronology protection conjecture. He suggested that the universe has a built-in safety mechanism, a form of cosmic censorship that prevents time travel on a macroscopic scale. Hawking wryly noted that we never see tourists from the future, and he believed there was a fundamental law of physics that made their visits impossible. The conjecture proposes that anytime a closed time-like curve is about to form, something will always stop it. Quantum effects would conspire to destroy the wormhole. A massive buildup of energy would vaporize the time machine just as it was activated. The universe would rather tear itself apart at the quantum level than allow a paradox to unfold. So while the white hole offers a tantalizing exit into the past, the cosmos itself may be permanently locking that door, protecting the orderly flow of time from the chaos of its own deepest secrets. That cosmic flash of light is not the only signal a white hole might broadcast across the void. Its violent birth or sudden death would shake the very fabric of space-time, creating ripples known as gravitational waves. Our most advanced observatories, like LIGO and Virgo, are now listening to the universe's gravitational symphony. They have already heard the characteristic chirp of two black holes spiraling together and merging into one. But what would a white hole sound like in this language of gravity? The signal would be utterly different. Instead of a rising chirp that builds to a crescendo, you would hear a sudden, sharp pop. It would be a single, explosive burst of gravitational energy, a shock wave from a single, catastrophic event. Imagine the difference between listening to a violin playing a long, drawn-out note and hearing a single, powerful drumbeat. The chirp of a black hole merger tells a story of a slow, gravitational dance over millions of years, ending in a final union. The pop of a white hole would be a story with no preamble, a tale that begins and ends in a single, violent instant. This unique fingerprint is what scientists are now listening for in the mountains of data collected by these incredible instruments. They are searching for that one anomalous signal that does not fit the pattern of any known cosmic collision, a gravitational shout from the dark that could be the first proof of a cosmic fountain turning on or off for good. White holes shatter the comfortable predictability of our everyday world. You cannot push against a wall without feeling an equal pushback, and a campfire cannot burn without consuming its fuel. These are the classical rules our intuition is built upon. A white hole breaks them all. It is a cosmic source that ejects matter and energy without ever appearing to consume anything from our universe. Where does it all come from? Its very existence seems to be a violation of conservation, a magic trick with no visible magician. Its time-reversed nature is even more disorienting. We are conditioned to see effects follow causes, but a white hole suggests the eruption itself could be the cause, reaching backward to orchestrate its own origin. This turns our linear experience of time into a local quirk, not a universal law. Confronting a white hole means abandoning the solid ground of classical physics and stepping into a realm where logic flows in both directions, forcing our minds to expand beyond comfortable limits to grasp a universe far stranger than it appears. This final cosmic era would unfold in a darkness deeper than any we can comprehend. The last red dwarf stars have long since cooled into black cinders, and the galactic supermassive black holes have evaporated away through Hawking radiation. The universe is a frigid, near-perfect vacuum, a graveyard of scattered particles and fading echoes. Yet in this profound stillness, a new chapter begins. The universe enters its white hole era. One by one, across the unimaginable vastness, the ancient remnants of black holes undergo their final transformation. Triggered by quantum processes operating over trillions upon trillions of years, each one rebounds. What was once a bottomless pit of gravity becomes a sudden, brilliant fountain. In the endless night, these popping eruptions of energy flash into existence like a string of cosmic firecrackers. Each one is a final, defiant burst of light and warmth, a rebirth of energy in a cosmos sliding toward maximum entropy. This is not a violent, chaotic period. The eruptions are isolated and fleeting, separated by gulfs of time and space so vast they make the current age of the universe seem like a single heartbeat. For a brief, glorious moment, a region of space is flooded with radiation, a temporary sun in a dead sky. Then it fades, leaving behind only a faint, expanding shell of particles. This would be the last active phase in the life of our cosmos, a final spectacular chapter written in flashes of light long after the last star has died and the last civilization has turned to dust. It is a poetic and haunting vision, a universe that ends not with a whimper, but with a series of brilliant, solitary pops. This singular point of infinite density is the ultimate failure of our physical theories. Yet white holes may offer an elegant escape from this mathematical dead end. The problem with the black hole singularity is not just its strangeness, but its impossibility. Physics cannot function where quantities become truly infinite. It is a sign that our understanding is incomplete, a glaring error message in the universe's code. The solution lies in the strange world of quantum gravity, where the smooth fabric of space-time is replaced by a grainy, discrete structure. In some of these models, the terrifying singularity vanishes. It is replaced by a core of extreme but finite density, a state known as Planck density. This is the absolute maximum density the universe allows, a quantum limit where matter and energy are packed as tightly as physical law permits. At this point, the relentless inward crush of gravity meets an immovable quantum wall. The collapse stops. The spring has been compressed to its absolute limit. And then it rebounds. This quantum bounce transforms the black hole's core into the heart of a white hole. The entire object undergoes a fundamental phase change from ultimate consumption to ultimate expression. In this breathtaking picture, the white hole is not a separate object, but the final, natural state of a black hole that has reached its quantum limits. It resolves the singularity not by ignoring it, but by providing a physical outcome, a cosmic release valve for the infinite pressure. The white hole becomes the universe's answer to its own most profound mathematical flaw, a graceful exit from the abyss. A white hole has no mind, no will, and no purpose. It is not a conscious gatekeeper or a sentient doorway to another dimension. We must resist the temptation to dress this cosmic object in mystical clothing. Its terrifying power and bizarre behavior are not the products of a cosmic intelligence, but the direct, unforgiving consequence of physical law. Every single aspect of a white hole, from its impenetrable event horizon to its explosive final burst, is governed by equations. It is a machine of pure physics, an engine of causality, even if that causality sometimes appears to run backwards from our limited perspective. The rules it follows may be the strange rules of quantum gravity or the inverted rules of time-symmetric relativity, but they are rules nonetheless. This distinction is vital because it keeps our feet on the solid ground of scientific inquiry, even as our minds reach for the stars. The true wonder is not that the universe might contain magical gateways, but that the sober, mathematical laws of physics can themselves give rise to something as seemingly miraculous as a white hole. Its mystery is not one of magic, but of a reality so profound that its logic transcends our everyday experience. The universe does not need mysticism to be awe-inspiring. The simple, brutal truth of its own laws is more than enough. The light from a white hole would paint a portrait of pure cosmic violence across every wavelength we can measure. To our most powerful telescopes, this would not be a single color, but a simultaneous scream of energy from one single point. It would begin as a low-frequency rumble in the radio bands, a deep hum of accelerating charged particles. This would be joined by a searing, brilliant glare of visible light, hot enough to outshine entire galaxies, but the true signature of its ferocity would be written in the highest energies. The eruption would blaze with intense X-rays and a torrent of gamma rays, the most energetic form of light in the universe. This full-spectrum broadcast is the white hole's autobiography. The specific blend of these wavelengths, the exact energy signature, would act as a cosmic fingerprint. It would tell us the temperature, density, and even the chemical composition of the matter being violently birthed. A spectrum rich in certain high-energy gamma rays might indicate the creation of heavy elements like gold and platinum in the forge of the eruption. A dominance of X-rays could reveal a plasma of electrons torn from their atoms, superheated to billions of degrees. By reading this light, we could decipher the recipe of the white hole's heart, understanding what kind of cosmic stuff it was made of, all from the rainbow of its catastrophic death cry. That initial burst from the Big Bang was powerful, but perhaps it was only the beginning. Cosmic inflation is the theory that a fraction of a second after creation, the universe underwent a period of unimaginably rapid expansion, ballooning from smaller than a proton to a vast cosmic landscape in less than a blink of an eye. This idea elegantly explains why the universe is so uniform and flat on large scales. But what could have possibly powered such an explosive, faster-than-light growth spurt? The answer might lie in the ultimate white hole event. Imagine the moment of the quantum bounce, the instant our universe rebounded from a previous state of collapse. That rebound would have unleashed a titanic, repulsive force, a gravitational pressure of pure creation. This is not the gentle push of dark energy we see today, but a violent, singular shove of space-time itself. In this radical view, the white hole eruption was not just the Big Bang, it was the trigger for inflation. The white hole's innate nature, its relentless outward pressure, provided the perfect engine to drive that brief, spectacular period of hyper-expansion, stretching the infant cosmos to its current immense size before settling into the more sedate expansion we observe now. This merges two of the most profound ideas in physics, suggesting that the most successful theory of the early universe and the most elusive theoretical object might be two different expressions of the same cosmic birth cry. This reversal of time forces us to confront the meaning of forever. Classical physics tells us that once a black hole forms, it is essentially eternal. It will sit in the cosmos for an endless duration, slowly evaporating over trillions of years but never truly ceasing to exist within any meaningful time frame. If a white hole is simply a black hole running backwards in time, then its existence must also be eternal, stretching infinitely into the past. This is a staggering conceptual leap. We are accustomed to objects having a clear beginning, a moment of creation. A star ignites, a planet coalesces, a black hole forms from a supernova. But a primordial white hole, in its pure theoretical form, would have no such starting pistol. It would have always been there, a cosmic fountain that never needed to be turned on, perpetually erupting since before time itself had any meaning we could comprehend. It exists outside the chain of cause and effect that defines our reality, an ever-present source in a universe of fleeting events. This challenges the very core of how we think about existence. Must everything have a start and a finish, or can the universe contain engines of pure being that simply are forever? The white hole dares us to consider a cosmos where some things are truly timeless, not as abstract concepts, but as physical objects woven into the fabric of eternity. The mathematics behind white holes is as rigorous as the theory that predicts black holes. We must be very clear about their scientific standing. These are not flights of fancy or science fiction concepts dreamed up to fill a cosmic plot hole. White holes are a specific mathematical prediction that emerges directly from Einstein's theory of general relativity. This is the very same framework that has passed every experimental test we have thrown at it for over a century. It correctly predicted the bending of starlight by the sun, the precise orbit of Mercury, and the existence of gravitational waves we now detect from colliding black holes. The equations of this incredibly successful theory do not just describe black holes. They present a complete picture of space-time, and within that picture, the white hole is a valid, symmetrical solution. The fact that our telescopes have not yet found one does not mean the math is wrong. It simply tells us that the universe is a very particular place. The conditions required for a white hole to form, or to persist long enough for us to see it, must be exceptionally rare or incredibly subtle. Perhaps they form and collapse in an instant, too quick for our instruments to catch. Maybe they are hidden in plain sight, disguised as more common cosmic explosions. Their absence from our observations is a puzzle, not a dismissal. It challenges us to look deeper, to build better telescopes, or to refine our theories further. The white hole remains a ghost in the machine of gravity, a persistent echo in our most fundamental equations, waiting for the right moment to reveal itself. Our inability to observe white holes directly does not mean we are blind to their secrets. We have built digital universes to explore them, vast computational realms governed by the precise laws of physics. Inside the world's most powerful supercomputers, physicists run complex simulations using a field called numerical relativity. Here, the equations of Einstein's theory are translated into billions of lines of code, creating a virtual laboratory where the impossible becomes tangible. Researchers can program a digital white hole into existence, setting its mass, its spin, and then watching in exquisite detail as its life unfolds over mere processor cycles. These simulations are not video games, they are rigorous experiments in a cosmos of ones and zeros. They test the fundamental stability of these objects, probing the moment a stray digital particle drifts too close. Does the simulation show the white hole collapsing into a black hole as theory predicts, or does it reveal a hidden mechanism for stability we have not yet imagined? The computers calculate the subtle ripples in spacetime that such an event would produce, mapping out the unique gravitational wave pop that would be its only cosmic hello and goodbye. They model how the white hole's relentless outward wind would push against and reshape a virtual cloud of interstellar gas, showing us what such a confrontation might look like through a telescope. Every simulation is a question posed to the universe, and while the answer comes from a machine, the insight it provides brings us one step closer to knowing whether these cosmic fountains are merely beautiful mathematics or a reality waiting to be found. This mirror universe of white holes offers a powerful lens for understanding the black holes we see. By studying the time-reversed version of a black hole, astrophysicists can isolate and examine the fundamental processes that govern these cosmic monsters. Take the brilliant, whirling disk of superheated gas that spirals into a feeding black hole. This accretion disk is a chaotic and complex system where magnetic fields, friction, and intense gravity all interact. Now flip the direction of time. That chaotic infall becomes a clean, explosive outflow. Theorists can model this white hole eruption to see how the components of a jet would behave if they were born from a central source and shot outwards, free from the messy complications of infalling matter. This gives them a clearer picture of how black hole jets, those narrow beams of particles traveling at near light speed, are launched and focused in the first place. It is like understanding how a fountain works by first studying a simple, powerful water jet before adding the complexity of the recycling pump and the basin. The white hole model strips away the chaos of consumption, allowing scientists to see the pure physics of expulsion, which in turn illuminates the hidden mechanics behind the spectacular jets we observe blazing from active galactic nuclei. Even the strange physics at the event horizon becomes clearer. The mysterious phenomenon of frame dragging, where a spinning black hole twists the very fabric of spacetime around it, must have a perfect mirror in a spinning white hole. By calculating how a white hole would drag and then expel spacetime, researchers can test their models for this extreme environment, refining our understanding of what happens in the turbulent region just outside a black hole's point of no return. The white hole, forever out of reach, acts as a cosmic laboratory in the mind, a theoretical tool that sharpens our vision of the dark hearts we are finally learning to see. This grand vision transforms the cosmos from a one-way street into an eternal, breathing entity. Black holes and white holes could be two halves of a single, magnificent life cycle, the ultimate cosmic recycling system. Imagine the universe not as a collection of isolated events, but as a vast, interconnected metabolism. A black hole acts as the cosmic stomach, a region of space-time that consumes and compresses matter and energy, locking away the information of everything it swallows. It is the gathering phase, the inhalation, but this is not the end. Through a process like a quantum bounce, that compressed information and energy is not destroyed. It is transformed, processed in the hidden forge of a singularity reborn. The black hole then becomes a white hole, the cosmic mouth, exhaling that same substance back out into the universe. The matter and information that vanished into the gravitational abyss is not lost forever. It is simply being reprocessed, its quantum story rewritten into a new form of energy and particles that bursts forth in a different location, or perhaps even in a different time. This creates a closed loop of existence, an endless cycle of death and rebirth on a cosmic scale. The star that died to feed a black hole in one galaxy could have its fundamental essence reborn as the raw material for a new nebula in another. The universe itself will be practicing the ultimate form of sustainability, where nothing is ever truly wasted, only endlessly transformed. This elegant cycle offers a profound answer to the fate of everything, suggesting that our reality is not headed for a cold, silent end, but is instead part of an eternal dance of consumption and creation, forever turning the old into the new. White holes captivate us not because they answer our questions, but because they magnify them. They are the ultimate symbol of the unapproachable, a cosmic fortress whose treasures are perpetually expelled, yet whose gates remain forever locked. This is a mystery that resonates on a deeply human level, touching our innate curiosity about what lies beyond the final boundary. We are drawn to stories of forbidden knowledge and unreachable realms, from ancient myths of sacred mountains where mortals cannot tread to modern science fiction tales of alien artifacts that defy all understanding. The white hole embodies this archetype in its purest physical form, a literal place in the universe where the rules of entry are absolute and final. It represents a creation that requires no consumption, a beginning without a visible cause, a gift from the cosmos that asks for nothing in return. This challenges our most fundamental understanding of how the world works, where every action has an equal reaction and nothing comes from nothing. The white hole whispers that our logic might be a local custom, not a universal law. It forces philosophy out of the classroom and into the stars, making us wonder if our entire experience of reality is just one small chapter in a much weirder book. The true power of the white hole is not in the light it emits, but in the profound darkness of our own ignorance that it illuminates, reminding us that the universe's greatest secret may not be a hidden truth, but the sheer, beautiful scale of what we have yet to learn. Our journey through the cosmos has taken us to the edge of comprehension, from the dark hearts of black holes to the brilliant, elusive fountains of white holes. We have explored how these theoretical opposites are two sides of the same profound coin, born from the same equations that govern gravity itself. We have considered the staggering possibility that our entire universe erupted from a primordial white hole, a cosmic seed from a larger reality. We have seen how these objects might whisper the secret of dark energy and challenge our most fundamental laws, from the preservation of information to the very arrow of time. Yet for all their mathematical elegance, they remain ghosts in the machine of the universe, their existence a tantalizing puzzle that pushes physics to its absolute limits. The cosmos guards its deepest secrets closely, and the white hole stands as a monument to our enduring curiosity, a reminder that the greatest discoveries often lie just beyond the edge of our understanding. So tell me, which of these 50 facts reshaped your view of reality the most? Let the conversation continue in the comments below as we all gaze up at the same mysterious stars. This cosmic silence will not last forever. Our search for white holes is on the cusp of a profound technological leap, with new eyes and ears poised to scan the heavens for their faintest whispers. The upcoming Laser Interferometer Space Antenna, or LISA, is not merely an upgrade to our current gravitational wave observatories. It is an entirely new kind of instrument, a constellation of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, linked by lasers. This incredible sensitivity will allow it to hear the low-frequency hum of the cosmos, a gravitational symphony completely inaccessible from Earth. Within this new sonic landscape, LISA could detect the sharp, singular pop of a white hole's birth or death, a gravitational shockwave with no accompanying stellar collision. It would be a sound unlike any other in the universe, a definitive crack in the quiet that could signal a cosmic fountain turning on. At the same time, the James Webb Space Telescope is peering into the deepest infrared universe, its gaze capable of seeing the faint, cold glow of the most ancient objects. It could spot the lingering infrared afterglow of a primordial white hole's final flash, a ghostly warmth hanging in the void long after its brilliant visible light has faded away across billions of light years. These two observatories, one listening to the ripples in space-time and the other seeing the faintest heat signatures of creation, represent our best hope for turning this mathematical ghost into a physical reality. Their combined data could usher in a new era of cosmic discovery, proving that the universe's most profound secrets are not hidden from us, but simply waiting for the right moment and the right technology to reveal them